Good evening to Alma. My voice is clear or any noise is coming? Any one of you, please respond in the WhatsApp or chat box. Yeah, joining. Yeah, good evening, Ma. Compared to previous class, now it is clear now? Yeah. So to rectify this, I have taken so much time, Ma. So today we will discuss about the signal to noise ratio of PCM. (14 marks question, Ma. This one is 14 marks question. So now I will open the document. You please tell me whether it is visible or not perfectly. Excuse me. I'm sorry. Yeah. Is that the document is clear to you, ma? Guys, any one of you please respond. This document. It is clear now? Yeah, okay, ma Vedavati. Thank you very much for responding. 28 viewers, 26. If at least 40, then I can start. Yeah, ma. Okay, ma Sucharita. Thank you very much. Guys, after this, I will share the digital communication playlist, ma, which is already available in the channel. In that digital communication playlist, except this topic, I have covered all the topics up to ADPCM. Okay, so I will share the link after this class. So that will cover the entire first unit, unit 1. If you have any doubt, you please contact me, ma, in the college or WhatsApp group or in the YouTube chat also you can ask if you have any doubt anywhere. I will provide the hard copy also to you guys. Okay. So better I will put it in the description also, PDF. Then it will be visible for other college students also. Yeah. So in the next class I will start the second unit, ma, in online mode itself, because 22nd. When is your mid exam, ma? Do you have any idea? Only 30 members. Link is seen by so many members, but they are not interested, I think so. Okay, you can see later also, no problem. Okay, ma, I will start, ma. Maybe April 1st or 2nd week. Yeah, ma. That's why if I finish first unit, second unit also in the online mode, or at least half of the second unit, then it is easy for us. We can revise the topics first and second unit first half also after completion of the 3 units of syllabus. Sixth or seventh, April 6th or 7th. Okay, okay, ma. Guys, liking the video is free of cost. Subscription is also free of cost. You need not to pay any amount, single price also. Not liking the video, not subscribing the channel also. Okay, no problem. Okay, ma, I will start. 35 members are there. So here the topic is quantization noise and signal to noise ratio of PCM system. We are going to see now. First of all, we will see what is the quantization noise. So let us assume that Q is the quantization error. Capital Q assumed as quantization error, and let small q is the sample of the quantization error, capital Q. So if we have the x, one variable, and sample value is, we will consider it as small x. Likewise here assume that quantization error as capital Q and small q is the sample of the quantization error, capital Q. Next, one more thing is the quantization error Q is varying uniformly between minus delta by 2 to plus delta by 2. So here, to get the probability density function of the quantization error, so we assume that the capital Q, the quantization error is varying in between minus delta by 2 to plus delta by 2. So without this assumption also, we have already seen that in the uniform quantization and non-uniform quantization topic, the quantization error, what is the maximum and minimum value of quantization error? It is plus delta by 2 is the maximum value, minus delta by 2 is the minimum value. That we have seen already. What are the characteristics? Okay, in the physical class we have seen that one. That's why the quantization error uniformly varied in between minus delta by 2 to plus delta by 2, that you know very well. Then the probability density function of quantization error is given as f q of q is equals to, generally the density function is represented like this, fx of x or fr of r, f q of q. So likewise we will represent is equals to 1 by delta. This one is varying minus delta by 2 to less than or equals to q less than or equals to delta by 2, 0 otherwise. This also you know very well. So that we have expressed the quantization error probability density function. So like this. Now to satisfy this condition, we ensure that the input signal does not overload the quantization error. So it should not overload the quantization error. Then the mean of the quantization error is 0. This also you know very well, mean of the quantization error is 0 and the variance of the quantization error is equals to mean square value. This is from the concept of RV, RP, RPTSP. Okay, and then sigma q square, this also a basic formula, sigma q square is equals to expectation of q square, that is mean square value we can say. So which is equals to integral, this can be written as e of x square is equals to integral minus infinity to infinity x square into fx of x into dx. Here why we have represented with q in place of x means here we are talking about the quantization error, that's why x is replaced with q, that's it. Capital X, wherever capital X is there, we have substituted with capital Q. Wherever small x is there, we have substituted with small q. That's it, ma. Remaining entire procedure is same. Okay. So integral minus infinity to infinity q square into here. So actually 1 by delta, f q of q is 1 by delta if we substitute the limits of minus delta by 2 to plus delta by 2, and it is 0 for otherwise. So here also we need to substitute the minus delta by 2 to plus delta by 2. Guys, here also whenever you are substituting the fq of q, substitute limits as minus delta by 2 to plus delta by 2. So this is the expression actually. So sigma q square is equals to 1 by delta into integral minus delta by 2 to plus delta by 2 q square into dq. So you know it, integral x square into dx is equals to x cube by 3. Likewise 1 by delta into q cube by 3. Limits, substitute the limits, then you will get del square by 12. Sigma q square. So here this sigma q square we will consider it as noise power. So signal to noise ratio means signal power to noise power. So here now we have the signal power. Now we need to get the expression for, noise power. Now we need to get the expression for the signal power. So what is the signal power? So now this is the signal to noise ratio of PCM. Let us consider a signal x of t whose power is p. Then the signal to noise ratio can be written as signal to noise ratio is equals to general expression signal power to noise power. Signal noise. Signal to noise ratio is equals to, so here we have considered signal power as P divided by, what is the noise power we got? That is from the expression number 1, del square by 12. So P by del square by 12, which is equals to 12P divided by delta square. So now we have the signal to noise ratio expression as 12P divided by delta square, where P is the signal power, that is x of t power, and delta is the step size. What is the step size? Any one of you guys, what is the step size? What is the step size? Not audible. Esma, Deepika, I think from your side there may be a problem. What is the quantization error? Any one of you please respond. Difference between the successive steps or successive rises. That is the definition actually. According to the expression, what is the step size? The ratio between the peak to peak voltage to the number of quantization levels is equals to the step size expression. So delta is equal, very important for 2 marks question. What is the step size? They will give the peak to peak voltage and quantization levels, calculate the step size. Very simple problem. Delta is equals to V peak to peak divided by capital L, where capital L gives the number of quantization levels, and which is equals to number of quantization levels expression is equals to 2 power n, where n is the number of bits in a code word. So if 6 bits code word is transmitting through a channel and the peak to peak voltage of the signal is 4 volts, what is the step size of the system? 4 divided by 2 power 6. That will give the step size. Okay. So likewise there is a chance to ask the question, very important for external exams and as well as for competitive exams also. Step size is very important. So to calculate step size, we need to get the number of quantization levels expression, 2 power n, and what is n, that also we should know. Substitute this 3 in expression number 2, signal to noise ratio. 12P divided by delta is V peak to peak divided by L whole square, which is equals to 12P L square divided by VPP square. Take this one as expression number 5. See here 1, 2 completed, 3, 4, 5. This one is the 5th expression. Now let us consider the input signal x of t is having the peak to peak value minus x max to plus x max. So generally any signal value, voltage value is varying between plus V max to minus V max. Here we have considered it as minus x max to plus x max. Then peak to peak voltage, signal to noise ratio is equals to 12P L square into peak to peak means V max minus of minus V max. Likewise we will consider, then it will become 2 V max. In terms of voltage I am telling So here likewise 12P L square divided by x max minus of minus x max whole square, which will give 2 x max whole square. This one is as it is 12P L square is from here onwards 12P L square, 12P L square. It is continuing. Next step is signal to noise ratio 12P L square divided by 4x max square. So 4 1 ja, 4 3 ja. Signal to noise ratio is equals to 3P L square by x max square. So this is the basic expression. Expression number 6 is the basic expression for signal to noise ratio of PCM. Basic expression. from this expression, by assuming some conditions, we will derive case 1, case 2, case 3 expressions of signal to noise ratio. So by applying some conditions, some normalization, some assumptions, we will get the 3 expressions. So this is the basic expression. What is the signal to noise ratio expression for PCM system is 3p L square x max square, where P is the signal power, L is the number of quantization levels, x max is the maximum input voltage. Okay, I think up to now it is clear, ma. So very simple, ma. So first of all, to get the noise power, what we have to do, assume the probability density function fq of q, that is varying between minus delta by 2 to plus delta by 2, the value is 1 by delta, substitute that one with the limits of minus delta by 2 to plus delta by 2, so q square into dq, then you will get the sigma q square as del square by 12. This is the noise power. Signal power, let us consider it as P, so P divided by del square by 12, 12P by del square. This is the signal to noise ratio actually. And what is the delta expression? V peak to peak by L square, substitute this in this one, then we will get the expression like this. After this, what is the peak to peak expression generally? Vmax minus of minus Vmax to Vmax. So that also we have substituted here. Then we got the expression for signal to noise ratio of PCM as 3p L square by x max square. I think up to now it is clear na guys? Low voice, not audible. Guys, any one of you please give me the response. Is it okay, ma? Low voice. Okay. I will try to increase the volume. Is it okay now, ma? Guys? Voice is okay? Yeah. Sucharita, I am asking to Krishnaveni and Obaya, Deepika. They are saying that low voice, not audible. Vedavati, is it okay now? Krishnaveni, are you there, ma? Ubaya, is it okay now? Yeah. So up to now, we have derived the expression for signal to noise ratio of PCM system. Very simple expression, ma. Yeah, okay, Krishnaveni. So if I increase the volume, we will get the resound. Okay. Yeah, okay, ma Obaya. Thank you very much for responding. Now we will see what are the cases of signal to noise ratio expression. So this is the basic expression of PCM system. Case 1, when input x of t is normalized. Normalizing means generally we will equate that value is equals to 1. X max is equals to 1 and power is also normalized. So case 1 we are assuming as input is normalized to 1, power is normalized, that is equals to 1. Then signal to noise ratio expression will become as P is equals to 1, X max is equals to 1, then it is equals to 3L square. From equation number 4, we know the number of quantization levels capital L is equals to 2 power n, where n is the number of bits in a code. Then the signal to noise ratio expression is equals to 3 into 2 power 2n. Is it right? L means 2 power n whole square, it will become as 2 power 2n. Let us consider this one as expression number 7. Now, the signal to noise ratio in terms of dB. Sometimes they will ask calculate in terms of dB or signal to noise ratio in terms of dB, or they will give the value in terms of dBs also. then we need to convert into normal value. Okay, so that's why we will signal to noise ratio we will represent in terms of decibels. Okay, which is equals to 10 log of 3 into 2 power 2n. 10 log 3 log a b ma, log a plus log b. So 10 log 3 plus, again this one is 10 log a power n, which becomes n into 10 log a. So then the expression will become 2n into 10 log 2. The value of log 3 and log 2 substituted here. So what is the value of log 3 ma? Any one of you from this expression? Any guesses? Log 3 0.477 ma. Log 3 is 0.477. By substituting with the 10, we will get 4.77 plus 2n into log 2 value is 0.3010. By substituting with, by multiplying with the 10, we will get 3.01. So 4.77 plus 2n into 3.01, then you will get 4.77 plus 6n, 3 into 2n, equated to 3 just. So the signal to noise ratio in terms of dB is equals to 4.8 plus 6n. Let us consider this one as expression number 8. If the condition in the problem is given as input is normalized, power is normalized, then we need to use this expression directly. No need to use this expression, main expression. So if they have given the condition on the input like this, then directly we can use this expression. In the problems ma, there is a chance to ask for competitive exams and as well as for external exams also very important. These all expressions, 3 expressions are very important ma. Okay, so I think it is clear up to expression number 8. It is clear na ma? Do you have any doubt anywhere guys? Shall I move to case 2? No, my idea is 0.477. Check it. Shall I move to next? Case 2? Yeah, guys, tell me, shall I move to next? Case 2. Any one of you, please respond in the chat box. Yeah, Viresh, okay, ma. Thank you for responding. Okay, ma. Srinath, you are also there. B section, second CR, na you are? Okay, ma. Case 2. When the input is sinusoidal, then the signal power P is equal to. So here, case 2 we have considered it as when the input is sinusoidal in nature. Input is sinusoidal signal. Then what is the expression for signal to noise ratio? So if the input is sinusoidal, then the signal power P is equals to V RMS squared by R. So generally for communication system, we will consider resistance as equals to 1 ma. Okay. So here V RMS is replaced with X RMS squared by R, and R is equals to 1. Then P is equals to X RMS squared, which is equals to RMS value generally V max by root 2. V RMS is V max by root 2. Likewise, X max divided by root 2 whole square. Why I have considered here in terms of X again, why not in terms of voltages? Because I have considered the signal to noise ratio varying from minus X max to plus X max. So So the expression is in terms of x max only. That's why here also I am considering in terms of x itself, not in the voltage. So then only the x max, that x max and this x max will get cancelled. That's why we need to consider in terms of x's. Okay. So x max square divided by 2. Substitute this in expression number 6. What is the expression number 6? That is basic expression ma. This one, basic expression. So 6, substitute capital P expression. Then we will get signal to noise ratio is equals to 3. P is this one, x max squared by 2 into L squared by x max square. X max square, x max square will get cancelled. 3 by 2 into L square. Again, in terms of dV, signal to noise ratio in terms of dV is equals to 10 log 3 by 2 L square. So log A by B means log A minus log B. 10 log 3 minus 10 log 2 plus this is again in terms of A into B. So A plus B, 3 by 2. This one is completed plus 10 log of L is 2 power n. So then you will get L square as 2 power 2n. Okay. Now if we substitute log 3, log 2 values, then we will get the signal to noise ratio expression as, see here, this one, do the simplification ma, very simple simplification it is. See here, 2n into 10 log 2, again substitute log 2 value, then you will get 3.01 into 2n. 1.76 plus 6n, and this is approximately equals to 1.8. Again for simplification purpose. So signal to noise ratio in terms of dB is equals to 1.8 plus 6n. This is expression number 9. So when we need to use this expression ma, 1.8 plus 6n, when the input is, when we need to use that expression, when the input is 1.8 plus 6n, when we need to use that expression, case 2, when the input is normalized or when the input is sinusoidal. Which option we need to choose? 1.8 plus 6n expression when we need to use, when the input is normalized or input is sinusoidal. A or B? A is input is normalized and B is input is sinusoidal. Give me either A or B. Sinusoidal. Very good, Sucharita. Yes, ma. When the input is sinusoidal, we need to use for SB. Very good, Vanita. Yeah. So that's about the signal to noise ratio expression of PCM system. Next, case 3. When the input is uniformly distributed. So from here to here, when the input is uniformly distributed from minus x max to plus x max. When the input is uniformly distributed from minus x max to plus x max, then we need to use this expression. When the input is uniformly distributed from minus x max to plus x max, then we need to choose this signal to noise ratio expression. How can we get that expression? See here, then the likelihood function will be given as fx of x is equals to 1 by 2 x max, where this is varying from minus x max to plus x max and 0 otherwise. Then calculate the mean square value like the signal power. Then you will get sigma x square as, sigma x square is equal to 1 by 2 into x max into 2 x max squared by 3. This one will get cancelled. This square, this one will get cancelled. 2 gets cancelled. Then you will get sigma x square is equals to, signal power is equals to x max squared by 3. There sigma q square, that is noise power, and here this one is sigma x square means signal power. Remember that point. Okay, P now become x max squared by 3. why again we are using in terms of X max? Why? Because the main expression is in terms of X max. Okay. Substitute this 10 and 6. What is 6 again? The main expression of the signal to noise ratio. So that is 3p L square. 3p L square divided by X max square. So this one is 3 and this one is p. This one is L square and this one is X max square. So X max square will get cancelled. 3 gets cancelled. Then we have only L square. So signal to noise ratio is equals to L square. Signal to noise ratio is equals to L is, you know very well, 2 power n, 2 power 2n. In terms of dB, you will get only 6n. Signal to noise ratio in terms of dB is equals to 2n into 10 log 2, which is equals to 2n into 10 into 0.301, which is equals to 2n into 3.01. Actually 6.01 into n, so that is approximately equals to 6n. When the input is uniformly distributed from plus Vmax to minus Vmax, or when the input is uniformly distributed between minus 5 volts to plus 5 volts, when the input is uniformly distributed between minus 3 volts to plus 3 volts, then we need to choose this signal to noise ratio expression, which is Cn. Very simple expression, when the input is uniformly distributed from negative value to positive value, then we need to choose this expression. That's it about the signal to noise ratio of PCM system. Do you have any doubt anywhere, ma? Very simple, ma. Step by step. First of all, we need to get the quantization error expression and sample value. Consider it as small q. Take the probability density function and let us consider 1 by delta between minus delta by 2 to plus delta by 2, 0 otherwise, and find the mean square value, that is equals to noise power. Consider the signal power as P, then we will get signal to noise ratio expression for PCM as 3p L square divided by X max square. Then assume the conditions, case 1, case 2, case 3. Okay. So in the problem they will ask the conditions on the input. Based on that we need to choose the expression, or otherwise they will ask derive the expression for the signal to noise ratio of PCM. Direct question, ma. 14 marks question. Okay guys. So is it okay? So if you have any doubt, you can ask me personally. Okay. Okay guys, thank you for attending, ma. Motivate your friends also to attend the future classes. I am going to end this session with this. Yeah, Akhil. Your number is 409, ma, Akhil. B section first number, I think so. Thank you, ma'am. Thank you, ma Krishnaveni. Okay, thank you, madam. Can you share the, yeah, I will share the PDF, ma. I will share the PDF in the description. I will share that video also, in which description I have given the PDF. Okay, 404. Okay, ma. Ma Srinath, Gnaneshwar are there. Gnaneshwar, are you there? B section CR, C section CR, motivate your friends to attend the classes, ma. Yeah, okay, ma. So I will share that PDF in the description of this video itself, ma. Okay, I will add that PDF to the description of this video. You can go through that. Okay. Okay, ma. Thank you very much for attending. I am going to end this session. Yeah. Okay, ma. Bye.